All right. So in this video, we will mostly look at how high dimensionality is actually a great thing and how it technically helps us out in the end, even though it looks really daunting, right? Like if you say that, oh, my last dimension is like 1 million dimensions, and how do I even know what's happening there, right? And it turns out that it's really good that we don't know what's happening there because it turns out it really helps us a lot, right? So let's look at how certain things work very differently in high dimensions. And often these topics are not talked about when we talk about traditional machine learning, right? And there are some misconceptions which kind of get carried forward where people learn certain misconceptions in their initial days of machine learning and they kind of take it forward with them when they scale up, right? Because there are certain things that work in 2 dimensions and 3 dimensions, but they don't scale very well. And that's not the scene when we go to like a million dimensions, or LLM models that we have nowadays are like 230 billion and whatever, right? So the landscape changes a lot, and we'll be looking at few things that are quite different. And as usual, we'll be looking at it from a very mathematical point of view. No hand wavy stuff here, right? All right. So the first thing, which is a huge misconception, is that local minimas don't really exist in higher dimensions. Um, and I'll try to explain to you why. So, what is a local minima, right? That let's say when you draw your loss curve, let's say if you draw a quadratic curve, right, it can have multiple minimas. Uh, and sometimes what happens is when you try to visualize how a gradient flows, you might think that, oh, this is going to get stuck at the local minima, but I wanted to get to the global minima and things like that. But that's not really what happens. Let's try to understand how this works mathematically and how uh, SGD works and all these things work, right? So let's try to have a in-depth look at how things work in high dimensions. Right. So this is a Taylor expansion of your loss function. So let's say you're at some point theta and you want to move by delta theta so that, you know, you go to the next position. You're exploring the landscape, right? The optimizer which you use essentially is just exploring the loss landscape and trying to find the best position and the best possible parameters for your model, right? And this is a very simple example. You can see there are only three parameters, theta 1, theta 2, and theta 3 for now. This is just so that we can visualize it. Obviously, we cannot visualize 4 dimensions, but let's look at the Taylor expansion, right? So this is a second order Taylor expansion where we are expanding it up to the third degree, I mean, up to the second degree. And we really don't need the third degree because the first degree dictates the slope, the second degree dictates the curvature, and the third degree and fourth degree and so on and so forth, they dictate things like wiggle and things like that, which generally we don't really need them. We can approximate functions with very good accuracy with the second order approximations in itself. So we don't really go for the third order approximation. So this gradient of L is the first order derivative, and H is also called as a Hessian in calculus. Hessian is a second order derivative. You can see here, right? It's a second order derivative. So if we have three parameters, let's just look at how this gradient looks like, right? So if you want to talk about this, this would look something like this: dl by d theta 1, dl by d theta 2, and dl by d theta 3, right? And the Hessian would look Hessian, that is the second order derivative, would look something like this. It would be a square matrix of d square L by d theta 1 square, d square L by d theta 2 square, d square L by d theta 3 square, and this would be d square L by d theta 1, d theta 2. And these are all partial derivatives, by the way. So that's something which we really need to keep in mind, right? D theta 1 and d theta 3. And you get the idea, right? So here the differentiation is how the landscape, how the loss changes with respect to both theta 1 and theta 2. And here it is with respect to purely theta 2, it's a second order derivative of theta 2. Here it's d theta 1 respect to d theta 3, and so on and so forth. So you can see how you can fill this 3 cross 3 matrix here, 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 and here, right? It's the same idea. Um, so the idea of the second order derivative is you calculate derivatives in pairs And in the first order derivative, it's just a simple partial derivative across a certain dimension, right? How can we say that local minimas don't exist? Like, that's a very radical thing to say, right? Because that kind of goes against the intuition that you have built up, right? So let's look at an example. So what is a local minima, right? A local minima is when you are at a point where any delta theta that you take forward would result in your loss going up, right? So if a point is a local minima, every possible delta theta must result in the loss going up. That's when you know you're in a local minima, right? So let's say you have three dimensions, right? So if you have to take a delta theta here, right? Very simple example. So if you have to take a delta theta here, this delta theta would have three components, right? Delta theta 1, delta theta 2, and delta theta 3, right? So there'll be three components. And similarly, if you go for higher dimensions, you'll have more components, right? If let's say you have 100 dimensions, right? So you will have a delta theta which belongs to 100 dimensions, 100 dimensional vector, right? Now, what happens is all these 100 dimensions need to simultaneously curve up. Only then your loss can increase, right? Because you want all your dimensions, any delta theta in any dimension should increase your loss function, right? So you want all your dimensions to be curving up. And that is a very low probable event, right? The probability of that happening is very low, right? Even if you take, let's say at a point, let's say you do this and this delta theta belongs to R100, right? And uh, let's take the fact that it's a 50% probability that your dimensions might go up or your dimensions might curve down, right? And 50 is me being extremely generous, by the way. Even if you take a 50% probability, that's 1 by 2, your chances, your probability of getting all of the directions to be going up is somewhere close to that. And that is extremely small number. And the more you increase this, the worse it gets because it's a denominator, right? So the more dimensions you have, the worse your chances are of actually finding a local minima because all your dimensions need to be curving up at the same time. And how can that even be possible, right? So, and if by chance that you even find a local minima, it might be the point where your data set is overfitting to the network, right? And that's why it probably looks like a local minima to you. So this is a big thing, and this is debunked, and I'm not pulling things out of thin air. It's proven. There's a paper. I'll attach it to the description of the video. And this is a proven fact that local minimas don't really exist in higher dimensions. And the mathematical way of looking at this is a matrix is positive semi-definite only if all of its eigenvalues are greater than zero, right? And only if a matrix is positive semi-definite can we say that, uh, it's a local minima, right? So the Hessian, which we talked about here. So if for all delta theta transpose multiplied by the Hessian multiplied by delta theta, for all delta theta that is not equal to zero, obviously if you multiply it to zero, it's going to be zero. For all delta theta, if this remains greater than zero, only then you can say that the Hessian is positive semi-definite, and only then can you say that you're at a local minima, right? So this is the mathematical way of looking at it, and this is the technical term which you should be using if you want to refer to a local minima, right? Now, if local minimas don't exist, then what sometimes we see the laws getting stuck, right? So what are those points and what are these other things that exist if local minimas don't exist? So there are two things that we need to like look at here. So the first thing is saddle points, and the second thing is plateaus or plateaus, or however you pronounce that word. So let's say your Hessian matrix has some eigenvalues greater than zero and some eigenvalues less than zero. That means the loss curves up in certain dimensions and the loss curves down in some dimensions. And when you look at all the dimensions, when you put them all together, they all just cancel out and you have a point of no gradient. So your gradients are essentially, the second order derivative is basically zero, right? So your Hessians are very, very close to zero. So the gradient at that point is very less. And what happens is your optimizer kind of gets stuck there because your optimizer needs a gradient to perform an update to your parameters, right? And there is no gradient at this point. So what happens is that your optimizer gets stuck and your network doesn't know how to process this point, right? Because your optimizer works on the logic of gradients, right? And but there are no gradients here. Um, right? So this is the first thing that most likely occurs, and mostly these large loss landscapes, they are filled with saddle points and plateaus. So let's also look at what a plateau is. And let's say the Hessian has many eigenvalues which are very close to zero. The gradient cannot provide any information to the optimizer. The optimizer is basically lost. It doesn't even know where it is anymore because it does not, there is not really a lot of information that this Hessian matrix is carrying, right? It's a very low rank matrix. And this causes your optimizer to kind of feel lost and not know what to do. And there are two major solutions which people generally use for this. So one is batch normalization, and this is the formula. It's pretty straightforward. It's just a scaling, and the idea is to have a bound on the eigenvalues so that you kind of, it's like a regularization to some extent. Like even though you cannot use that term formally, it is a type of regularization where you are putting a bound on the eigenvalues. The other thing is skip connections, where obviously we know what a skip connection is, right? Let's say you have a layer here and you have an input here, and let's say you have an output here. A skip connection is basically this, right? So where you concatenate the output. So what input of the previous layer to the output, so that the idea is when you do an fx plus x, your network is forced to learn this residual instead of learning entire concept or a sequential concept. It's kind of compartmentalizing your network so that each part can learn a residual concept instead of learning the entire gradient, right? Because when you differentiate this, you can see how you can have a persistent gradient, which always keeps the gradient strong. And this helps in kind of reducing the plateaus. And there is a really interesting paper which came out about the skip connections in ResNet and how it smoothens out the loss landscape, and it helps in really easier learning, especially when you're using an optimizer like SGD. Now, since we are on the topic of SGD, let's also discuss another thing, how SGD and Adam works better than Newton's method. And Newton's method is nothing too complicated, is where you use the Hessian to perform on optimization. And we discussed what a Hessian is, right? A Hessian is the second order derivative of the loss. So SGD assumes that your Hessian matrix is an identity matrix. So in our case, an identity matrix would be 1, 1, 1, 0, 0, 0, 0, 0, and 0. So this is what an identity matrix. And we are saying we are going to assume that our Hessian is like this, right? What this means is d square loss by d theta 1, d theta 2 is 0. D square loss d theta 1, d theta 3 is 0. But d square loss by d theta 1 square is 1. So let's try to understand what this means. This means that theta 1 and theta 2 are independent because there is no value there. Theta 1 and theta 3 are independent. Theta 1 only depends on theta 1. Theta 2 only depends on theta 2. Theta 3 depends only on theta 3. And all the other ones are 0. That means we are assuming, so, and I'm not making this up, this is how the SGD algorithm works, right? We are assuming that the second order Hessian is an identity, which means all the parameters are independent of each other. And this is an assumption that SGD makes, right? This is not true. This is obviously not true. Let's say you have a 10-layer neural network. Your 10th layer, the parameters in your 10th layer obviously depend on the parameters in your first layer, right? That's just obvious because the first layer processes information and it goes on to the second layer, third layer, and so on until the 10th layer. And the 10th layer parameters obviously depend on the first layer parameters. But SGD assumes that all parameters are independent. And this approximation works. And that's the beauty of high dimensionality. Because when you're working in high dimensionality, you can get away with, the best word to use is mathematical negligence. And this is basically mathematical negligence, right? Because you are saying something like uh, all parameters in your network are independent, right? But it still works. And you know what's funny? If you use the Newton's method, that is, if you actually calculate a Hessian, when you're on a saddle point, you're gonna get stuck because there are no gradients, right? Because the Hessian will go to zero and your network will always get stuck on saddle points. But using this approximation, that does not happen. So, in a way, if I had to informally rephrase this, SGD is mathematically not rigorous. In fact, you can also say that it's a dumb approximation, but it works because we are dealing with high dimensions. And we can get away with such crazy approximations in these high dimensions. So, and Adam stores a moving average of the gradients, right? So that's what we call as momentum. Some people call it velocity and things like that. So that's how we use this cache which we store to get over these saddle points and these plateaus. And that's how Adam works. And Adam kind of, if I had to like give you a hint on how it works, Adam does not really approximate it to an identity, but Adam tries to approximate this by calculating the momentum and storing gradients. It kind of approximates this in a different way where it's not really identity, but we try to circumvent this by using another mathematical approximation, which obviously we can discuss that in maybe another video. But this is the beauty of high dimensionality. A lot of people have this misconception of local minima, and I honestly attribute it to the fact that that's just how we are taught. Because when we are taught machine learning or deep learning, we always go through these examples of x square and 4x square where there are two dimensions, and it's obvious why the assumption is made like that. But this is not true, and this is very clearly proven that high dimensionality is what really helps us and helps us get away with a lot of approximations. Well, that's all from me for today, and I hope you found this video interesting. I'll try to bring more interesting topics like this that really pique my interest, and I don't want to talk about the generic topics because there are like 1,000 videos out there. And I hope you guys found this video informative, and well, peace.